Okay, so the plan for today is just to start chapter 5 on discrete probability distributions, continuing on with our kind of theoretical background side of things. I posted a couple of supplements on chapter 4 late last night. One is just a little 5-minute talk about just kind of how decks of cards and things work that I mentioned that I was going to post. And then another wraps up the chapter 4 counting section and the whole of chapter 4. And then I'll probably also post an additional maybe 30, 45 minute or so supplement on chapter 5 today or tomorrow. I'll probably cover either binomial distribution or Poisson. I might try to cover both in a supplement, just depending on how the time looks. So coming up, we have the midterm exam. That's the week of 3/18. So what would that be? 2 Mondays from now. And it'll be available or open that whole week. So it'll be kind of similar to how the Examity practice exam was structured, that it's just kind of posted and it's available. You can log in at your convenience anytime during the week of the 18th, anytime from that Monday through that Sunday, and take the exam using WebAssign and Examity and all of that. If you haven't taken the Examity practice exam, I strongly recommend you do that, this week or next, get that kind of out of the way, get all that technology sorted out, and just make sure everything's working properly before the week of the 18th, just so that if something, isn't working right, we have plenty of time to get it sorted out. And then lastly, the sample. Yeah.
Sorry.
No.
Do we have to schedule the midterm, or is just during that 1 week, anytime we want to take it, we can do it?
Yeah, so I think because it's automated, you don't really have to schedule it. I think Examity might still ask you to schedule it. Like it might give you an option to schedule it, but because it's completely automated, it doesn't really matter. It's much more important if it was like a live proctoring thing where there has to be a person on the other end. Then it's much more important to schedule it well in advance. But since it's completely automated and all that you're doing is logging into Examity's system and basically generating a recording on their servers, it really doesn't matter either way. Yeah.
Okay.
But they might still ask you to schedule it. I'm not sure, but if you feel like scheduling, you can. If you schedule it and you want to change the day or time, that's probably not an issue. So yeah, because it's all automated, that shouldn't be an issue. And so also the sample midterm exam is posted on my stat lab. It'll be at the top of the page. I put the exams at the top of the page just so they don't get jumbled in with all the homeworks that get added to the bottom of the page. So when you go to the assignments page, you'll see the exams at the very top. So the sample midterm exam, there's the Examity practice exam, and really the whole purpose of that is just to get you on the Examity system, get Examity hooked up with my stat lab, make sure the password thing is, working okay, make sure your camera's working well and all of that. There's a couple of dummy questions in that exam, but they're really just to give you something to do for a couple minutes just to make sure that everything's working. The sample midterm exam is a sample of something similar to the midterm exam. So it's going to be an exam that is not password protected. You don't take it with Examity or anything like that. But it's just meant as kind of an assessment, a self-assessment of how well you understand the material for the midterm exam. So it's a similar length of the midterm exam, similar types of problems, similar difficulty. So if you go through the sample midterm exam, and I usually recommend taking it in pretty much the same way that you're going to take the actual exam. But if you go through and you basically treat it like a test run of the exam, and you feel comfortable with all the material on it, you're happy with your grade, you should be pretty well set up for the midterm exam. If you go through the sample midterm exam and maybe there was a topic that you really got stuck on that you didn't expect, or something took a lot longer than you really thought it was going to, then maybe that points out some topics that you might want to review, you might want to practice a little bit, and you can retake the sample midterm exam as many times as you want. I will send out.
Sorry, another question. And where can I find the sample midterm exam? Is it on my stat lab or Blackboard?
On my stat lab. And so that's what I was saying. At the on the assignments tab, it'll be at the top of the assignments tab. So where the homework sections are added at the bottom of the assignments tab on my stat lab, the exams will be at the top just to keep them kind of separated out and easy to find on exam day.
Well, I'm on my stat lab right now on assignments. The first thing is examity practice exams, not the midterm practice.
Let me make sure that I have things right on my side. Let me log in really quick here. I think I need to adjust. Yeah, thank you for pointing that out. I need to adjust something. Okay, there we go. I need to change one setting. And then you should be able to see it. So just give me 1 second here. All right, now if you reload the page, you should be able to see it. So
sample mechanism. Now, yes, now I can see it.
yeah, okay, yeah. Thank
Yes,
you for
thank
pointing
you.
that out. Yeah,
Thank
yeah.
you.
I just had a setting. I had the start date for it as a future date instead of whatever date I had went in and did all of the changes. So I must have missed adjusting the start date when I did that. But yeah, thank you for pointing that out. So the sample midterm exam is
Yep.
now available in my stat lab. And again, that's a very similar exam to the actual exam. So the purpose of the sample midterm exam is to practice the material for the exam. The purpose of the examity practice exam is to practice the examity process. So just to keep those two separate for you. And then again, I'll send out a Blackboard announcement with kind of all the details laid out a little more thoroughly. But I think, I think it's a pretty standard kind of straightforward setup once you go through the examity practice exam and the sample midterm exam. There shouldn't be any surprises on the actual exam. All right, any questions on anything about the exam? You can use a calculator, you can use Excel or StatCrunch or both if you want. You can use a formula sheet. So there will be a formula sheet that will be uploaded in the examity system to use on the exam. But I'll also make the formula sheet available on Blackboard. So just so that there's less stuff to do on exam day when you're in examity and all of that, I'll have the formula sheet on Blackboard, and then you can just download that to your desktop as a PDF. That might be easier for you to do it that way. Or if you want to, you can print it out. If you want a physical page just sitting there next to you, that's fine too. But you can use, the physical page, the PDF, the one that comes through examity, whatever works best for you. So formula sheet, calculator, you can use scratch paper, blank scratch paper, pen, pencil. Yeah, basically the only things that you can't use are another person or like other web pages or things like that, other internet resources. But and like no book, no notes, those kind of things. But you can use the formula sheet, calculator, Excel, StatCrunch. So whatever you're more comfortable with using as far as computations go is fine. Okay, so let's start into chapter 5. Oh, and the quote of the day today, particularly applicable to stats, is by a somewhat controversial historical figure. So I'll leave it unattributed. But there's the quote that one physical test is worth 1,000 expert opinions. And I thought of this. I was hanging out with somebody last night who I'm friends with, and he's an economist, and he works in kind of housing and real estate and research in that kind of area, which is obviously a big hot topic today. And I had this idea, this theory that I was like, hey, I've been thinking about this for a little while now, housing market craziness, like, what do you think about this idea? Is this like, does this seem to be actually borne out in the data? Because one of the difficult things with economics is actually gathering data and crunching data and doing the stats to, that just takes a lot of time and effort and expertise. But he's like, yeah, like what you're saying kind of makes sense based on the fundamentals. Like it seems like that would be a plausible argument, but we actually just don't see that borne out in the data. Like, when we look at the data, this is what we see as kind of the factor that's causing this or that thing to happen, rather than what you're saying. So, so I had my expert opinion or my whatever opinion based on some theory, and it's just simply wrong. So empirical evidence for empirical sciences is everything, whether that's in something like economics, where you say, hey, I have this really cool idea, it's a really beautiful mathematical model. It's like, okay, it doesn't match up with reality. Well, it's not the right model. I don't care how nice it is. And then the same thing goes with even a hard science like physics that's very close to the metal, so to speak. Economics is a little more of a social science, what they might call a soft science. But something like physics, you can repeat experiments very carefully, lots and lots of times, and so on. And same thing, I could have a really beautiful mathematical model that comes out of a ton of theory, and I have a really good reason for it. But if you run the experiments in the lab and they don't mesh with your model, the model's wrong. You can't say that reality is wrong and your model is right. So that's always something to keep in mind, particularly as we start talking more about the kind of theoretical side of things. We're developing models. We, in a sense, for these couple chapters, cloister ourselves away from the real world, and we say we're just building up this mathematical structure. That's all well and good, but at some point we want to talk about, like, examples of rolling dice or something like that. And if I have a model and it's discordant with what I experience in reality, then my model's wrong. Reality is probably not wrong. Although I'm sure many philosophers would debate that. Maybe Plato would debate that. I don't know. But anyway, so I think this is always something to think about. This kind of goes along with the idea that some models are wrong, or all models are wrong, some models are useful. Somewhat related to that idea. Okay, so moving on to chapter 5, discrete probability distributions. We talked about the idea of probability, and we set up some of the foundational concepts in probability in chapter 4. And we talked about computing probabilities in chapter 4 when we had a sample space with outcomes that were equally likely. And we had some structures that lent themselves fairly well to that model. Things like rolling a fair die, flipping a fair coin, things of that nature. But what if I have something that's kind of fundamentally where I have fundamentally unequally likely, is that the right way to say it, outcomes? So what if I had something like this? What if I had a die that I wanted to roll, six-sided die just like before, but this die is weighted a little bit wonky. It was manufactured a little strangely. So for instance, the number 4 comes up 25% of the time, more often than we would expect, and the number 1 comes up only 10% of the time, less often than we would expect if it were a fair die. So we see that we can't just say, okay, what's the probability of rolling a 3? That's 1/6, because there's one way to roll a 3, and there are 6 ways. There are 6 outcomes for this probability experiment. We can't do something that simplistic. We have to take a slightly different approach. Now, one way that we can imagine kind of forcing this into the mold of a fair die, or sorry, of a sample space with equally likely outcomes into the type of model that we had for a fair die. We could imagine we have a bag of outcomes. And with a fair die, we would just have, say, slips of paper in here labeled 1, 2, 3, 4, 5, and 6. We'd have 6 slips of paper, each labeled 1, 2, 3, 4, 5, or 6, one slip per outcome. We'd reach in, grab a paper, one paper at random, and that would be our die roll. We could imagine an experiment looking something like that. For a system like this, where 1 through 6 are not equally likely, we could kind of imagine if I had a bigger bag, if I had, say, a slip of paper, we'll call it slip 1, another slip of paper, slip 2, 3, and so on. So if I had, say, 100 slips of paper, and let's say this is slip 10 over here, 11, and so on. I have 100 slips of paper. And maybe what I'll do is I'll write a number on them, like the number 1 for the outcome. Each one of these slips of paper will be drawn 1% of the time. So if I want 1 to be drawn 10% of the time, I'll write a 1 on 10 of the slips of paper. And then I'll start writing 2s on the next 10 slips of paper, and then 3s on the following 20 slips of paper, so that 20% of the time 3 will be drawn. 4 will be on 25 slips of paper, 5 on 20, 6 on 15. Or if I was a little slicker, maybe I could recognize that I could get away with only using 20 slips of paper and, keep the ratios the same. I'd have 2 slips out of 20 with a 1 on it, 2 slips out of 20 with a 2 on it, and so on. So I could imagine generalizing my basic probability structure to something like this, where I just have a bunch of different outcomes, where this outcome is like drawing slip of paper number 1 that has a 1 written on it. And this outcome is like drawing slip of paper number 3 that has a 1 written on it. So my equally likely outcomes are the slips of paper rather than what's written on the slip of paper. So in a sense, I'm building off of that previous structure, but I now have kind of 2 things that I'm interested in. The drawing of the slip of paper is the equally likely outcome, but then the number written on the slip of paper is what allows for the variability in the ultimate likelihood of what number I read on the slip of paper I draw. So that's our goal in chapter 5, is to generalize the concepts in chapter 4 so that we can deal with distributions with probability experiments that, at least in some sense, have unequally likely outcomes. Okay, so what is a discrete probability distribution? Well, a probability distribution is an assignment of different outcomes to their probabilities. So I can enumerate, in this case, all of my outcomes, 1 through 6, and I assign a probability to each one of those. So that's a probability distribution. And it's a discrete probability distribution because for each outcome, I can say, what is the next outcome? Right. If we were thinking of something like, say, height, if a person's height is 6 feet tall, what's the next possible height? Well, it's not 6 foot 1 inch. It's not 6 foot and half an inch. It's not 6 foot and 0.1 inches. There's no next height, right? So we're talking about discrete versus continuous variables here. chapter 1 coming up again. So we're thinking of these outcomes here as being discrete. Typically, in this class, we're also going to deal with finite distributions. So most of the time in chapter 5, we're going to deal with situations where we can enumerate all of our different outcomes. I can list them all in a table, at least in theory. Maybe in some situation, there's a whole bunch of them. Maybe there's 200 and I don't want to list them all, but at least I could. Now, there are situations in discrete probability distributions where if I was, say, counting the number of heads until I get a tail on a bunch of coin flips, well, I could get one head before getting a tail, or 100 or 1,000 or 1,000,000. In that case, we still have a discrete probability distribution because there's still the idea of a next one. You know, I could get one head before getting a tail. The next one would be getting 2 heads before a tail. The next would be 3 before a tail, and so on. But it just kind of never ends. So I couldn't really enumerate it fully in a table. But for the most part, we're going to be dealing with finite discrete variables. Chapter 6 is going to move into continuous probability distributions, and we'll have to make some adjustments when we get to that chapter. So to be a discrete probability distribution, our outcomes must be discrete quantitative. And also we have this law of total probability, kind of reminiscent of chapter 4, where our list of probabilities has to sum to 1. So in other words, if I run this probability experiment, something has to happen. If I roll the die, I have to get 1, 2, 3, 4, 5, or 6. And that also means that if I was, say, missing one of these probabilities, if I didn't know what this one was, the requirement that the sum be 1 tells me what it has to be. I can add up all of the other probabilities and then say, what does this have to be to add to 1? And it would have to be 15%. One thing that that people sometimes get, I guess, confused about with probabilities is they think that if there are 2 outcomes or whatever, that they always have to be equally likely. And if we think about this for even just a second, we know that that's not true. But a lot of people want to impose that on the system. They want to say, oh, okay, because you're rolling a die that has 6 sides, you know, the chance of rolling a 1 is a 1/6, or the chance of rolling an even number is a half. But that's only true if it's a fair die, right? So we don't want to think that if there are 2 possible outcomes, the chance is always 50-50. I mean, certainly we can see that, like, we could consider an event, win the Powerball or don't win the Powerball. If I buy a Powerball ticket, you know, win the jackpot versus don't win the jackpot. And I don't think anybody thinks that it's a 50-50 chance of winning the jackpot. But for less extreme examples, sometimes people will make this assumption, and that's not a good assumption to make. So some examples of probability distributions, discrete probability distributions. We could have a random variable counting the number of heads on one flip of an unfair coin. On one flip, we could either get 0 heads if it came up tails, or we could get 1 head if it came up heads. And we could, for instance, have a probability associated with that. Maybe for this particular coin that we have, it's a little imbalanced. So it comes up tails 30% of the time and heads 70% of the time. So this would be a discrete probability distribution for this variable. So here we have kind of our coin, comes up tails 30% or heads 70% of the time, and X in each of these cases, which counts the number of heads, is 0 or 1. So we have something that's qualitative that we're making quantitative. The qualitative is, did I get a heads or tails on a given flip? And we're making it quantitative by, say, counting the number of heads on this one flip. We have something similar in this next example where we could have a random variable representing the winnings on a bet of $1 on an unfair coin where we bet on heads. So again, my coin flip could result in tails or heads. Again, it comes up tails 30% of the time, heads 70% of the time. In this case, my winnings on a bet of $1, if I bet $1 on heads and it comes up tails, my winnings are negative $1. If I bet $1 on heads, it comes up heads, I'm betting even money here. My winnings are positive $1. So for the same kind of underlying structure, this flip of this coin that is unfair in a certain way, we could have different random variables associated with that have different probability distributions. Here we have -1 or +1. Here we have 0 or 1 for my outcomes, right? How do I take this qualitative outcome and translate it into something quantitative to get a discrete probability distribution? So again, two things that we tend to be interested in, whether it's from chapter 3 or chapter 4 or now chapter 5, is what is kind of something like the mean of the distribution, what's the typical outcome, and then maybe what's the volatility, what's the range of plausible outcomes. So the idea related to the mean of the distribution, and we actually even give it often the symbol mu, but the mean of a discrete probability distribution, it also gets this notation, the expected value of X. So the E with square brackets is the expected value operator. And what goes inside of it is the random variable that we're interested in taking the expected value of. And what we see here is that the expected value is just the weighted mean. It's the outcome weighted by the probability. Each of those added together. Remember that for a weighted mean, we would often have some numerator divided by some denominator. But in this case, the denominator is, say, probability of x1 plus probability of x2 out to probability xn. But remember, these probabilities from up here have to sum to 1. So this denominator we don't have to write out because the probabilities all sum to 1. So this expected value is just the weighted mean of the outcomes, where the weights are the probabilities. So these are the weights, the probabilities of the outcomes. Another way to think of the expected value is it's a center of mass. If I had a weightless rod and I had locations on that rod, say starting from some 0 point, if I had x1, x2, x3, x4, out to say xn. And if I placed a mass at each of those locations related to the probability, so I place a mass m1 here that's of size probability x1. I place a mass m2 above position x2 that's size probability x2, and so on. And if I find a center of mass, if I find a balance point where I can balance all of these masses on this weightless rod, that location will be the expected value of x. So it's the center of mass of this distribution in this sense. Now, something that's a little bit unfortunate about the term expected value, you might think to yourself, okay, like if you knew nothing about statistics and I just gave you this setup here, or let's say this setup, where you either lose $1 or win $1, and I say, what's your expected value? You'd probably think, well, maybe my expected value is just like winning $1 because that's what happens the most often, right? Maybe that's what I expect to happen most often. And that's not really what the expected value tells us. The expected value tells us the center of mass. So just like the mean tends to not be an actual data point, it tends to not actually be a data value that we've observed. The expected value tends to not be an actual outcome. So the expected value of this distribution would be between -1 and +1. And the same way that this balance point is typically not going to be right at one of these locations. It's going to be somewhere in between some of the masses. Okay, so to compute an expected value, what do we need to do? We need to take each outcome, multiply by its probability, and then add them together. So let's find the expected value for our two coin flip distributions, the one where we count number of heads on one flip and the one where we bet $1 on that coin flip. So I have my list of outcomes with their associated probabilities. The first thing I need to do is multiply them together. And I think to keep things orderly, the best way to do this is to append another column onto the table, just kind of like we did in chapter 3. These columns won't be the same columns as in chapter 3, so be careful about that. But we're going to just kind of make some more columns to help us with the calculations. I need to multiply the outcomes times the probabilities. So 0 times 0.3 is 0. And 1 times 0.7 is 0.7. And then I have to add down this column. I have to add up the outcomes times the probabilities. To get my expected value. So my expected value is something like 0.7 heads per flip. And again, on a given flip of a coin, can I get exactly 0.7 heads? Well, no, I either get 0 heads or 1 head. What do I mean when I say that my expected value is 0.7 heads per flip? Kind of what I mean is that if I repeated this probability experiment a bunch of times, if I flip this coin, 10,000 times, then on average, I would expect to get something like 7,000 heads out of those 10,000 flips. So that's what I mean by an expected value, kind of like a long-term average rather than a short-term result on a single run of the probability experiment. If we look at the random variable that's the winnings of a $1 bet on the unfair coin, same structure, betting on heads, same probability. Multiplying across, -1 times 0.3 is -0.3. +1 times 0.7 is plus 0.7. And my expected winnings is 0.7 minus 0.3 is plus 0.4. My outcomes are in units of dollars. So this third column is in units of dollars. My expected value is also in units of dollars. So my expected value, my mean, is in units of the original data as I would want. And I see that I actually have an edge here. This means, so my expected value is plus 40 cents per play. This means that kind of on average, if I play this game thousands of times, on average, I would win 40 cents per play. Now, on a given play, I either win a whole dollar or I lose a whole dollar. But if I repeated this game lots and lots and lots of times, and then averaged together all my winnings and losses, I would end up with about 40 cents per play to the better. So this would be a game that I would want to play because it's to my benefit, at least in some sense, right? If I was willing to take the risk of losing a dollar, it seems like this is in my benefit. So this might be a game that's favorable to me. Now, if the game is favorable to me, the person that I'm betting against, presuming that they actually know this is an unfair coin, and I'm not like, defrauding them or something, they might not want to play this game. How can we make this an even game? How can we make it so that the expected value is 0 so that neither one of us has a long-term edge and it's kind of a fair game that way? Well, one way would be just to use the fair coin. So we would have, in that case, symmetry between the payouts. And if we replaced the unfair coin with a fair coin, we'd have symmetry in the heads versus tails. This has got to be a fair game. What if we didn't have access to an unfair coin, or to a fair coin, if we just had this unfair coin? We could keep this asymmetry, but we could change the payout to make it a fair game. Right. To set this balance point in a certain place, I could either change the size of the masses or I could change the locations of the masses. I could either change the probabilities or I could change the outcomes. In this context, changing the probabilities would look like using a different coin. If I only had this coin to use, I could change the locations of those masses. I could change the outcomes. I could tell my friend, okay, well, I realize that tails doesn't come up as often. So if it does come up tails, I'll pay you more than $1. And if it comes up heads, you pay me $1. That kind of incentivizes them to take the less likely option. And we might want to know, how much would I have to offer to pay my friend to make this a fair game based on this unfair coin? So if I'm betting $1 on this unfair coin, I'm betting on heads. What would I have to offer my friend? What would I have to pay my friend when it comes up tails to make it a fair game? Let's say that's the D dollars. So I either win minus D or I win +1, depending on if the coin comes up tails or heads. So multiplying across, I get negative 0.3 D plus 0.7. And my expected winnings or 0.7 minus 0.3 D. And I would like to choose D so that this equals 0 to make it a fair game. So neither of us has a long-term advantage or disadvantage. And this gives me D equals 7/3, or about $2.33. So this would be a fair game, at least approximately. If I said to my friend, okay, well, tails comes up 30% of the time, heads comes up 70% of the time. If we flip the coin and it comes up heads, you pay me $1. But if we flip the coin and it comes up tails, I'll pay you $2.33. Then it would be approximately a fair game. Okay, and then let's consider this unfair die from before. We still have our 6 outcomes, but the probabilities are not equally likely. The probabilities are not all the same. So we could do the same thing here. If we're looking for the average or the expected number that comes up on this die, we can append a column to our table. We can multiply across. 1 times 0.1 is 0.1, 2 times 0.1, 0.2, and so on. Or we could use Excel. We could use a calculator. We could use Excel. Let me bring up Excel here. And get my screen share switched over. Oh,
Real quick, on the test, so you know how in our stat lab we can pull up Excel, it has a little icon for it. Will we have that option on the test too? Will it be able to do that with Examity?
do you mean the stat crunch in my stat lab? Or
Yeah, for like our homework, you know how there's like that little thing and then you can click on hit open in Excel. I didn't know if
okay,
it would.
yeah. So where you can like move the data over to Excel, you mean?
Yeah.
It should, I think it should, yeah, all of that should work. Examine shouldn't like lock down anything. It's not set to like have a lockdown browser or anything like that. So yeah, Examine shouldn't interfere with any of that functionality.
Okay, thank you.
Yep, sure. So let's see if this will copy over. See if Microsoft cooperates with Microsoft. There we go. And I could work all of this out. I could do the product of these in this third column, and then the sum. So equal sum. If I want to add up a bunch of cells, and I see that my expected value is 3.8. So on average, when I roll this die, if I rolled it a whole bunch of times and averaged my results, I would get an average somewhere around 3.8, I would expect. I can also use a built-in Excel function, the sum product function. And this computes something that is sometimes called an inner product. I can just pick my first list, comma, my second list. And what this will do is it will multiply the two lists together, component by component, and then add. So it does exactly what we want it to do. We get 3.8 from there as well. So sum product can be a nice little function to use sometimes. Sometimes it's helpful for things like this. So we can use Excel for more cumbersome calculations. Smaller ones I would just do by hand. I don't think it's really worth moving something like this over to Excel. But for something like this, maybe this might be borderline case. But certainly if I had 10 or 20 or something lines, I would pop that into Excel and either just make my third column here or use the sum product function to get my expected value. Okay. So any questions on what a discrete probability distribution is or what expected value is, how to compute it? Okay, so then moving to the next topic, section 1 in chapter 5 is kind of a pretty big section. So introducing the idea of discrete probability distributions, going through expected value, and also discussing variance of standard deviation. Okay, so in this context, what is the variance? Well, the variance of x is the average squared deviation from the mean. Okay, so what's a deviation from the mean? That's like my random variable minus mu. My squared deviation from the mean is my random variable x minus mu squared. And the average in this context, in the context of probability distributions, an average is an expected value. So this is our formula for the variance. It's the expected value of x minus mu squared. In practice, this can be kind of annoying to compute directly. So we also have a form that's a little nicer to compute, especially to compute by hand. So we need to talk about a couple of things. First off, well, up above, we talked about what is expected value of x, but what about expected value of some function of x? How do we compute that? Whether it's either this one where I have to do x minus mu all squared and compute its expected value, or this one where I just have to compute expected value of x squared. So that's the first thing that we need to think about. And then the second thing we want to think about is why can I rewrite this formula in this way? So let's take a minute and talk about those nodes. So the expected value of a function of x, expected value of g of x, nicely enough, taking expected values of functions of x is just as simple as replacing each outcome with the function of x. So remember that the expected value of x is x1, probability of x1 out through xn, probability of xn. If I want to find the expected value of g of x, I just replace each of my outcomes like x1 here. Zoom keeps popping stuff up. Sorry, it's distracting me. I replace x1 with g of x1 out to xn with g of xn. And in particular, if I want to, let me bump this down one line. In particular, if I want to find the expected value of x squared, instead of having an x1 here, I just have x1 squared. Instead of having xn, I just have xn squared. So that's not too bad. It's just the same old expected value calculation like we did up here, but I just replaced the X column by maybe an X squared column, or if I wanted to do it more directly, by an X minus mu squared column. Something else to note is the expected value is a linear operator, meaning that it split sums apart and constants can come out of it. So in other words, the expected value of a times x plus b, where a and b are constants and x is a random variable. Well, from up above, we know that we've applied a function to x. We take x, we multiply by a, then add b. If I want to compute the expected value of that transformed random variable, I just apply that transformation to each of the outcomes. I take x1, multiply it by a, add b. Same for x2, out through xn. Note that it's very important that my probabilities are not transformed. Probability of x1 is probability of x1 everywhere, whether it's in my original expected value or in the expected value of the transformed random variable. The probabilities have to stay the same, because if I go transforming my probabilities, they might not add up to 1 anymore. And then I would lose the context of this being a distribution and expected value and so on, and a weighted mean and all of that. If I rearrange these, I can split off the ax terms from the b terms. So for instance, I have ax1 times probability of x1 plus ax2 probability of x2 and so on, plus b times probability of x1 plus b probability of x2 and so on. I can factor the a out, factor the b out. Next to the b, in these parentheses, I just have the sum of all of the probabilities. That's just 1. So this is just b times 1. And next to the a, I have just exactly expected value of x. So the expected value of a times x plus b is a times the expected value of x plus b. So the expected value splits sums apart and constants can come out. We call that a linear operator. The variance of x is the expected value of x minus mu squared. If I multiply this out, this is a binomial, x minus mu all squared. If I FOIL this out, I get x squared minus 2 mu x plus mu squared. So that's where this comes from. The expected value split sums apart. That's one of the things we just saw. So this is expected value of x squared plus, and I just put this as plus, an expected value of minus 2 mu. I just kept the minus inside to make it a little cleaner with the arithmetic for this part. Expected value of minus 2 mu x. And then the expected value of mu squared. Well, mu is a constant. What's the expected value of a random variable that's always a constant, right? Or if I had just one mass at one location and that was the only thing here, of course, the expected value is just that location. Or if I had a bunch of slips of paper and they all had exactly the same number written on them, what's kind of on average, if I draw a slip of paper, look at it, write it down, put it back, and do that a whole bunch of times, on average, what number will I get out of here? It's just going to be that one number. So the expected value of a constant is just that constant. So the expected value of mu squared is just mu squared. So that's where this comes from. This minus 2 mu here is a constant. It can come out of the expected value. That was the behavior of the a up here. So we have expected value of x squared, just copying that down, minus 2 mu expected value of x plus mu squared. But remember, we're using the terms mu and expected value of x now to mean the same thing. Mu equals the expected value of x. So this expected value of x here next to this minus 2 mu, that's just a mu. So I have expected value of x squared, just copying it over. Have to keep closing these Zoom pop-ups that it keeps popping up. I need to figure out how to get it to stop doing that. So expected value of x squared, we just copied over. Minus 2 mu times mu, or minus 2 mu squared, and then plus mu squared that we just copy over. So then I have minus 2 mu squareds plus 1 mu squared. That's a net minus 1 mu squared. So this is how we get from this definition for the variance, which is kind of the sensible definition, to something down here that's maybe a little easier to compute. It's a little easier to work through. So that's where this formula comes from. And as an exercise, show that the variance is not a linear operator. Show that the variance follows a different set of rules. It's not that the variance of ax plus b is a times the variance of x plus b, but the variance of ax plus b is a squared times the variance of x. This kind of makes sense. If we're just talking about the spread, adding b to the random variable just means take each outcome and shift it by a certain amount. If we just have this spread and we shift it over a little bit, the spread is still the same. If I say take each outcome and multiply it by a scaling factor, that increases the spread. So I would expect that to impact the variance overall. And I see that that impact is in the sense of a square. So when the a inside of the variance comes out in front, it comes out as an a squared. And we are familiar with from chapter 3 that the variance kind of inherently squares things. So that's what we're seeing, that behavior pop up again here. Okay, so let's compute the variance of standard deviation for these two distributions. Oh, and I think I didn't explicitly say it, but just like before, the standard deviation is the square root of the variance. Right, the variance has the same issue that it's in units, in square units of the original data. So we square root to get back to units of the original data. Very similar idea to chapter 3. Okay, so here we had the expected value, aka mu, was 0.7. We computed that up above. And now what I want to do, I want to compute the variance of x is the expected value of x squared minus mu squared. So I need to start by computing the expected value of x squared. And to compute the expected value of x squared, I take each of the outcomes, square them. That gives me a new column. And then I multiply those squared outcomes or probabilities, add them together. That gives me expected value of x squared. And then to get my variance, I have to subtract off the square of the mean. So here are my outcomes. If I make a new column where I square the outcomes, I actually get the same numbers. 0 squared is 0, 1 squared is 1. I multiply my squared outcomes against the associated probabilities. Again, do not square the probabilities. If I were to square the probabilities, squaring numbers less than 1 makes them smaller. And then my probabilities, or my squared probabilities, would no longer add to 1. I no longer have a weighted mean. Right? So I don't want to square the probabilities. I just multiply this column by the original probability column. 0 times 0.3 is 0. 1 times 0.7 is 0.7. Expected value of x squared is the sum of these two. 0 plus 0.7 is 0.7. Then the variance is expected value of x squared, which is 0.7 minus mu squared. Or this is 0.7 minus 0.49. Or I get variance of x is what? 0.21. And again, this is kind of like in square units. So then I would just go to my calculator and square root 0.21 to get a standard deviation. Or that's about 0.46 units. So my mean number of heads per flip is 0.7 heads per flip, with a standard deviation of 0.46 heads per flip. And we notice we could actually achieve 0 or 1 heads per flip. 0 heads per flip would be a little less than 2 standard deviations below the mean. 1 head per flip would be a little less than 1 standard deviation above the mean. That seems pretty reasonable, right? So we could do a similar calculation down here. Here's our winnings on a bet of $1 against the dollar. We already computed our expected value, our mean. The mean was 0.4. AKA the expected value. And now again, we want to compute the variance. And one thing to just be very careful about here, we need to be super careful about the notation and what all of this means. Note that this is not expected value of x all squared. That we can't like pull the square outside or anything like that, because if we did, this would just be mu squared minus mu squared, and that would just be 0. Clearly the variance is not just always going to be 0. So we just have to be very careful about the notation, what we're asking for in each case. So expected value of x squared says square each of the outcomes, multiply by their associated probabilities, then add together. That's the expected value of x squared. So -1 squared is +1. +1 squared is +1. We multiply by, again, the original probabilities. Don't square the probabilities. 0.3, 0.7. And then the expected value of x squared is 0.7 plus 0.3 is 1. The variance of x is expected value of x squared minus mu squared, or 1 minus 0.4 squared. That's 1 minus 0.16, which is 0.84. For the variance. And the standard deviation is square root of 0.84. And if we go to the calculator to get an approximate answer, we get about 0.92. And again, an outcome of +1 is the mean plus a little less than one standard deviation. It's a 1 sigma event. And an outcome of -1 is the mean minus a little more than one standard deviation. So it's a 1 to 2 standard deviation event, not unreasonable outcomes to get. Okay. Any questions so far? Okay, then let's jump over to Excel to help us with this one here. So I want to do the same thing, but I see that like figuring at x squared, these numbers are going to be kind of big. I have to multiply by a bunch of different probabilities. We're going to use Excel to help us here. So I have my, maybe I'll put it on this other side. I have my expected value of x of 3.8 listed here. This is my third column that I've appended. Maybe I'll color it blue so that we keep this color scheme kind of going. I want to compute my variance of standard deviation, so I need to compute my expected value of x squared first. So I need to compute my x squared column. And maybe I'll color these green just to keep the theme going. So I'm going to take my outcome and square it. To square, we just use the caret symbol, or to, if we wanted a cube, we would use caret 3 instead or whatever. So shift 6 gives you this caret, this like up arrow kind of thing. And then we put in 2 in order to square it. Or if you forgot that, you could kind of manually create a square by just multiplying the cell by itself. So if you forgot that that was the symbol for getting an exponent up there, you could just, in this case, multiply it by itself. I'll drag down and I see that my cells copy down that formula by relative reference. My last column has got to be, whoop, it did something wonky there. My last column has got to be the x squared times the original probabilities. Again, super careful not to square the probabilities. Oh. So my last column, x squared times its probability, or that's going to be that number times its probability. So 1 times 0.1 is 0.1. 4 times 0.1 should be 0.4. If I drag down, that looks good. So here's my rightmost column. These are the individual terms in my expected value of x squared. Each of these cells is like one of these xi squared probability of xi's. I need to add those together. And that gives me the expected value of x squared. Then what's my variance? My variance is the expected value of x squared, that cell, minus the square of the expected value. My variance is 2.26. And what's my standard deviation? It's the square root equals SQRT of the variance. So I get a standard deviation right about 1.5. So for this distribution, my mean is just under 4, standard deviation of about 1.5. I see that an outcome of 1, 3.8 down to 1 is 2.8 units. That's just about 2 standard deviations. An outcome of 6 is about a little more than 2 units above 3.8, the mean. That's a little more than 1 standard deviation above the mean. Again, we see that for kind of pretty reasonable distributions, really most or all of our outcomes are within 2 standard deviations of the mean. Yeah, that's not a problem. If you ever pop in late or have to leave early, no problem. You don't have to. Let me know. Yeah, you can just check out the recording. Okay, so using Excel helped us quite a bit here. We, saved ourselves some of the cumbersome calculations by hand, but we see we have the mean of 3.8, standard deviation 1.5 for this unfair die. So any questions so far? So one of the, I guess, positives is that this is about the most calculation intensive or formula intensive, I think anyway, part of the course. At least it feels that way to me. There are some formulas later on and things like confidence intervals and so on, but I think there's a little bit less steps to computing those formulas. For this one, to compute the variance, we need to first compute the expected value, then compute expected value of x squared, then take the difference of those expected value of x squared minus the square of the mean, then square root to get this standard deviation. There's just a lot of steps you have to do in the correct order. So this is probably the height of the difficulty of what I kind of call the bookkeeping side of things, just keeping all of the operations straight and doing everything in the right order and all that. Like I said, there are some formulas definitely later on in the course too, but I think those ones maybe flow a little bit better. It's a little more obvious what you have to do in what order and so on. So the technical complexity, I don't think it keeps going up and up and up. I think we've about peaked here. The theoretical complexity and understanding what the implications of say a confidence interval hypothesis test are, that's where it gets a little more complex later on. Okay, let's take a look at this distribution here. We have a random variable x, 0 or 1. So this could again be something like number of heads on one flip of an unfair coin. Let me actually jump back over to OneNote and try to close down Excel and see if that will get Zoom to quit pestering me. Maybe I'll close down the calculator too. Okay. Zoom keeps popping up a pop-up saying that it's not happy with how fast it's running, and it doesn't seem to be having a problem on my end, but hopefully it's not having a problem on your end. The only problem is that it keeps popping up this pop-up that I have to close down. So, okay, so this could be something like number of heads on one flip of an unfair coin, where probability of heads equals P. The sum of the two probabilities has to be 1, so the probability of tails has to be 1 minus P, so that 1 minus P plus P equals 1. And then I can compute the expected value. 0 times 1 minus P is 0. 1 times P is P. 0 plus P is P. I could compute the variance. X squared, if I square 0 and 1, I get 0 and 1 back. Multiply by the probabilities. Expected value of X squared is also P. And the variance of X is P, this one here, minus P squared. Or it's P times 1 minus P. So if I have a coin that comes up heads, probability P proportion of the time, and tails the rest of the time, and if I'm counting the number of heads, if that's what my random variable is doing, on one flip of the coin, that random variable has a mean of P and a variance of P times 1 minus P, or a standard deviation of root P1 minus P. There's an interesting idea called maximal entropy. In fact, my wife was just on a kind of a Zoom meeting this past Saturday with some colleagues. She's on this kind of national committee. And one of the folks on there was a mathematician, and he actually deals with maximal entropy distribution. Specifically, she was telling me about some of the stuff that he was talking about. So, but this idea of maximal entropy, we'll see some of these distributions that we have, like the binomial distribution in this chapter, or maybe the next chapter, the uniform distribution or the normal distribution. And you might say, well, like these are specific distributions. These are what we call canonical distributions that we use as kind of general models to model real life phenomena a lot of the time. Why would we use a normal distribution, or why would we use a binomial distribution? And sometimes the answer is that it has this so-called maximal entropy property. In science, there's an important idea called the law of parsimony, that if we can have a simpler model to explain the phenomena that we see, then that tends to be better. In other words, if we overlay fewer of our own assumptions and modeling assumptions and biases and so onto the system, we probably have a better model. So the simpler model tends to require fewer assumptions, and that's fewer things that can actually go wrong. If I make an assumption and it doesn't actually hold in the real world, then that's a way that my model can fail. So the idea of a maximal entropy distribution is saying, if I know something about a system, maybe I know what its mean is. Maybe I know the mean of a random variable, but I don't know anything else about it. And maybe I think I know the mean because, let's say I went out and collected a sample, big sample, and I took the sample mean, and I think that I have a pretty good idea what the population mean is now. Well, then what distribution should I assume about the, or not assume, but presume maybe, about the system as a whole, if say all that I know is the mean, or if all that I know is this or that characteristic of it? What would be the model that I should pick that, in a sense, imposes the least extra modeling assumptions other than what I already know about the system? And that's where this idea comes in. This turns out to be an important idea when we get to the section on confidence intervals. If we're missing a little bit of information, how do we kind of fill in that information in a way that's conservative, in a way that even if that information turned out to be kind of the worst case scenario, the prediction that I make will still hold true? And that directly ties to this problem that we just did here. What does the variance look like as a function of P? I know that P is a probability. P is between 0 and 1. When P is 0, the variance is 0. Of course, right? Because that's a coin that is impossible to come up heads. It always comes up tails. Variance is 0. There's no variation. We just always get a tails. We always get 0 heads per flip. Same thing if P is 1, then 1 minus P is 0. If my coin can only come up heads, if every time I flip it, it comes up heads, if every time I flip it, the number of heads per flip is 1, there's 0 variance. It just is always 1. And P minus P squared, in terms of P, that's a quadratic opening downwards. I know the maximum is at the vertex, and the vertex is right between the two roots here at 1/2. And at value P 1/2, we have a maximal height of 1/4 for the variance. 1/2 times 1 minus 1/2, 1/4. So P equals 1/2 gives the maximum variance. In other words, a fair coin coming up heads and tails equally likely gives me the, in a sense, maximum uncertainty about what's going to happen. A coin that comes up heads 90% of the time, I know that most of the time it's going to come up heads. If it comes up heads and tails 50-50 on one flip, I really don't have any good reason to pick one or the other side. So the maximum variance occurs at a fair coin at probability 1/2. Any questions on anything we talked about today? Okay, I think we're going to end a couple minutes early today. We got through section 5.1, a pretty big section. Again, keep an eye out on the next day or two for a supplement on chapter 5. I haven't exactly decided what I'm going to post and what we'll cover next week, but I'll take a look at where we fall on the schedule, and then might do binomial distribution or Poisson or both. And then next week, we're going to talk about Bayes' theorem. So at the end of chapter 5, we'll talk about Bayes' theorem and some of its implications, and a little bit of a different perspective of how we can look at probability rather than something like a long-term average. The Bayesian perspective is just a different take on what a probability means. So that's what we'll look at next week. And then the midterm exam the week of the 18th, 2 weeks from now. And again, later this week, I'll post a Blackboard announcement with a little more information about the exam. But I think, most of what we talked about today probably clarified most of the details for the exam. Just make sure to get the Examity practice exam out of the way early so that if any tech issues pop up, there's plenty of time to work those out.